Hello everyone and welcome to the video for section 9.8, Polar Equations of Conics. The skill objectives for this video are number 1, to define conics in terms of eccentricity. Number 2, express conics, equations of conics in polar form. And 3, graph the polar equations of conics. The conceptual objective for this video are to define all conics in terms of a focus and directrix. And that's really the big difference here. In the previous sections when we defined the parabola, ellipse, and hyperbola, the only conic we defined in terms of a focus and a directrix was the parabola. But that's going to change now when we're looking at the equations for the polar equations for conics with the hyperbola and the ellipse as well. You'll see in a second. Now, first, what we want to do is identify this alternate definition for conics. So when we do this, what we want to do is we're going to define some letters here, capital letters. Okay, first we're going to let D is a fixed line, and we're going to call that the directrix. Capital F is a fixed point that's not on the directrix, and that is going to be called the focus. And we're going to let E, little lowercase e, be a fixed positive number, which is the eccentricity. Notice this looks similar to Euler's number, which you are familiar with from logs. But it is a similar thing, but it's not being used in the same way. Okay, first up, we're going to go through and we're going to define this little d of PF. That is going to be the distance. D is distance from a point P on the conic and the focus. So it's distance from a point P to the focus. And we're going to let P capital D be the distance from a point P to the directrix. And so the way we're going to do this, we're going to have the set of all points such that if we take the ratio of those two distances, the distance from P to F and the distance from P to D, that's going to be our constant E. That's going to be equal to the eccentricity. In other words, this equation right here. Now, if E equals 1, then we know we have a parabola. If E is something that's less than 1, it's going to be a positive number. Keep that in mind. If E is less than 1, it's going to be an ellipse. And if E is greater than 1, we have a hyperbola. That's really how we're going to end up looking at these things. Okay? Now, before we move into actually going through and taking a look at what these equations are going to look like, some things that we're going to do is that we're going to keep in mind here. Number 1, we're going to locate the focus at the pole. We set these things up for our sake in terms of keeping these things fairly neat and easy to work with. The focus is going to be at the pole. Number 2, the directrix is either going to be parallel or perpendicular to the polar axis. Remember, the polar axis is like the x-axis. It's that horizontal line that goes through the pole on the polar grid. And with this, because of these two definitions here, these two ideas, we're going to have 4 different scenarios. That directrix is either going to be perpendicular to the polar axis, and and P units to the right of the pole, or the directrix would be perpendicular to the polar axis and P units to the left of the pole. The other thing is we could have the directrix parallel to the polar axis, and then it's going to be P units above the pole, or the directrix could be parallel and P units below the pole. So there's really the 4 different situations. 2, when we have a perpendicular directrix, in other words, a directrix that has an equation like x equals some number, and we're doing parallel, we're going to have y equals some number p. Okay, so those are the 4 different things. And again, whether or not you're dealing with P is a distance in this case, in both cases. So when you are, that can make a change in terms of what you're looking at. So if y was equal to -4, if we were using like y equals -4, the actual value should actually be kind of the absolute value of P. P would end up equaling 4. That would be the distance from the focus to the pole, or focus to the directrix. Okay, let's take a look at the derivation of these equations. Okay, now this is what we have. We have this graph here, okay? Now notice what I have. I have a conic here in yellow. I'm not defining what that conic is, okay? I have some conic here, and the green point is our focus. This line right here is our directrix. This distance is P, and this distance here is the distance from point P to the directrix, and the red line represents the distance from the focus to that point as well. Well, a couple things to keep in mind. The distance from the pole, or the focus here, which is at the pole, and a point P, that is always going to be equal to whatever R is. Remember, that's like that radius that's come out. We have the concentric circle. So that's just going to be equal to R. Whatever the R value of that, whatever that length is, that's R. That's going to be that distance. Now, this distance here is going to be P, and now you'll see I have P plus Y. Now, why do I have P plus Y? Well, in this case, I know that this distance from here to here, that distance is Y, okay? But also in this, Y is a negative number. So the whole distance is going to be P plus that negative number is going to give me that result. It's going to end up being the subtraction that's taking place. So that'll be P plus Y. That the plus there is because Y is a negative number. And P then would be, if I remember that in polar coordinates, Y is R sine theta. So this distance from point P to the directrix is equal to little p plus R sine theta. And so by the definition of the eccentricity is the ratio of this distance over that distance. So we have that R over P plus R sine theta. And really what we want to do now is solve for R. So to do that, I multiply both sides by P plus R sine theta. So I have R equals E times that P plus R sine theta. I distribute the E inside. And then I subtracted ER sine theta from both sides, I get to here. Okay? So now I have this equals here. Now I want to solve for R. So I'm going to pull out a common factor. So I have R times the quantity of 1 minus E sine theta equals EP. And then I divide by 1 minus E sine theta, and I got R equals EP over 1 minus E sine theta. Now the thing to remember on this, P is the distance from the pole to the directrix, and E is the eccentricity of our conic. Now this form here is going to be, this form works when we're dealing with a conic where the directrix is parallel to the polar axis and below the focus. Now, in each situation, of 4 different situations, is going to result in 4 different equations. Let's go take a look at those now. So here's what we got. When we have a vertical directrix, then we're going to be using one of these 2 equations here. R equals EP over 1 plus E cosine theta. We're going to use that when the directrix is vertical and P units to the right of the pole. And it makes sense because that's positive there, because to the right would be positive, to the left would be negative. And where P units to the left, we're using that negative one. So EP over 1 minus E cosine theta. The same thing is going to be true when we're dealing with a horizontal directrix. In that case, when we're P units above the pole, it's going to be 1 EP over 1 plus E sine theta. The plus above is addition, is positive, and when we're below the pole, that's going to be the negative. So we have 1 minus E sine theta. So those are 4 forms of these things. And you're going to want to kind of keep those in mind. Get those written down someplace that you can refer to them quickly. I'd probably put them at the top of the homework assignment too, so you can refer to those there as well. Let's take a look at some examples. Okay, now, in this first example that we have, okay, I know I'm given this information. I'm given that E is equal to 5, 6, and X is negative 3. Okay, so a couple things I know here. Number one, my directrix is vertical, and it's to the left. And I'm dealing with an ellipse because 5, 6 is less than 1. And so I know because it's vertical and to the left, R is going to be E times P over 1 minus E cosine theta. I now have to just plug the information in. E is 5, 6. Remember in this case, with what we're working on here, that P is going to be the absolute value of the negative 3. So P is 3. Because P is a distance, it's always going to be a positive number. And so when I plug everything in on this one, I have that R equals E is 5, 6 times 3 over 1 minus 5, 6 theta. I multiply the 5, 6, and 3. 3 does go into 6 twice. So that's how I ended up with the 5 halves over 1 minus 5, 6 cosine theta, like I have there. Now, the only other thing that they would end up doing on this one, because when you take a look at this, they're not going to have the fractions there. So what I'm going to do now on here is I'm going to go and multiply top and bottom by 6. And when I do that, 2 does go into 6 3 times. So in this case, for this one, I'll get R equals 15 over, when I multiply through by 6, I'll get 6 minus 5 cosine theta. And there would be the equation for this ellipse on this particular problem. Take a look at this next example. E equals 1, so we know it's a parabola. Y is equal to 4. Okay, I want you to go, pause the video right now, take a minute, identify which form it's going to use and plug everything in. Come back, we'll take a look at what you got. Welcome back. So on this particular problem, E was 1, and Y, the key thing here was Y equals 4. So that tells me that we are dealing with a horizontal directrix, and it is above the focus, so it's above the pole. So in this case, the form we're going to use is R equals EP times 1 plus E sine theta. I'll replace the E's with 1. P is equal to 4. And so I get 1 times 4 over 1 plus 1 sine theta. Or R equals 4 over 1 plus sine theta. And that would be the equation for that particular conic. Now, another thing that they're going to ask you to do, they're going to give you a conic, an equation like we have here, and they're going to ask us to go and from here solve this one, identify what this conic is, and identify then what is the value for P, how far is the directrix, what would be the equation for the directrix, all the different pieces from that. So the main thing you want to remember here, number one, you know in these equations, in the standard equations, that number right there, that is always going to be 1. Each one of them is 1. So I know in this case that I'm going to end up going through and dividing by, on this first one, I'm going to divide everything by 2. And when I do that on this problem, I will get that R equals 3 over 2 over 1 minus 3 over 2 sine theta. And now the other thing I have here, I know that the coefficient, when I do this, when it's in this form, the coefficient on my trig function, in this case sine, is going to be equal to E. So in this case, E is 3 over 2. And I know up here that the numerator, that numerator I know in this case is equal to EP, the E times P. So both of these are the same. So on this problem, I know that E is equal to 3 over 2. E times P is also equal to 3 over 2. So therefore, P is equal to 1. So in this case, I have a hyperbola. And I know the distance from, in this case, my directrix, the directrix in this case is 1 unit, and since it's a minus here, it's 1 unit below the pole, 1 unit below the focus. Let's take a look at this next example. Same idea. We're going to go through on that one, and we're going to get a 1. So when I do that, I'm going to divide everything by 5. I'll be 1 over 1 plus 4 over 5 cosine theta. So in this case, right now, it's pretty close. I know that this one is going to be is going to have a vertical directrix, and I know that we're dealing with an ellipse here because that E is equal to 4/5. So I know right now on this one E equals 4/5. And now I need to find out what P is. Well, I know that 4/5 times P is equal to 1. So therefore, P would be equal to 5/4. So on this problem, we have a vertical directrix. The directrix on this one is going to be x equals 5/4. The focus, again, is the pole, and we have an ellipse. With that, this does conclude this video. And we'll take a look at going through pulling out some of the other information. Remember, if you're going to go through and graph these, remember, in this case, the ellipse is the ellipse on these things. You also have to remember that E is also equal to C/A, where C, again, is the distance from the center to a focus, and A is the distance from the center to a vertex. So if you wanted to go out and find additional information on this, you know that C/A is equal to 4/5, and then you could solve that for B from there, and that would give you the information you need to go and sketch this thing in terms of a rectangular form. So with that, we conclude this video. We'll take a look at another example in class, and with that, enjoy the rest of your evening, and we'll see you in class.